Hello, students, and welcome. Today we're going to tackle a really important topic, and an interesting one too, the preparation of aldehydes and ketones. So, let's get started.
All right, to get us thinking, let me ask you a question. Just imagine for a moment, you're a chemist working in a big pharmaceutical lab, and your task, a very important one, is to create a vital ingredient for a new drug. How do you make sure you get it exactly right, with no errors?
Well, the answer to that big question, it all comes down to one single word: control. And this control comes from a process called controlled oxidation. Please remember this word, control, because it's going to be the main theme of our entire discussion today.
Okay, so let's start with our first section. We're calling it a chemist's essential recipe. And here, we're going to understand the why behind the reactions. So, you might be asking, why do we need to care about this topic? Well, it's because understanding it teaches us how to make these compounds, aldehydes and ketones, with real precision. And this is an absolutely essential skill when you're planning those long, multi-step syntheses in the lab. It's a very practical skill and very important for your exams, too.
Right. Now let's get to the core idea itself, oxidation. What is actually happening down at the molecular level?
At the simplest level, the idea is very straightforward. All we are doing is taking alcohols and performing a controlled oxidation on them, and from this we get either aldehydes or ketones. That's the whole summary in one line.
Now, to help you visualize this, imagine the oxidation process is like you are carefully stripping electrons away from the alcohol molecule. See, we are not breaking the whole molecule apart. We are just gently removing some electrons to change it into something new.
Okay, that's the simple idea. But for your exams, you will need the proper definition, so listen carefully. In this context, what is oxidation? It is a process where we break a CH bond, specifically the one that is adjacent to the OH group, and at the same time, we form a new CO double bond. And that chemical we add, the oxidizing agent, its job is to accept those electrons that the alcohol is giving up. All right, so our next section is about choosing your starting material, the alcohol. This is a very important choice because the structure of the alcohol you start with is what determines the outcome. Let's be absolutely clear about the three types of alcohols we can use. First, we have a primary alcohol. On the carbon atom that's holding the OH group, it has two hydrogens. Got it? Two. Then, a secondary alcohol has only one hydrogen on that same carbon. And finally, a tertiary alcohol, it has no hydrogens attached to that carbon. This difference, this number of hydrogens, is the most critical point. And this leads us to a very common mistake that many students make. There is a confusion that tertiary alcohols can also be oxidized to form ketones, but the fact is, they cannot. And why not? Think about it. To form that carbon-oxygen double bond, we said we have to remove a hydrogen from that carbon. But a tertiary alcohol simply has no hydrogen there to give. So, no hydrogen, no reaction. It's as simple as that. Please remember this. Okay, so we've chosen our alcohol. What's next? This section is on the importance of control, choosing the right tool for the job. And by tool, I mean the right oxidizing agent. This is where that word control becomes so important. Here's an analogy to help you remember the difference. Think of a mild oxidizing agent like a controlled burn, the kind firefighters use. It's very careful, very precise, and it stops exactly where it's supposed to. In our case, that's at the aldehyde. But a strong oxidizing agent, well, that's like an out-of-control forest fire. It just burns through everything in its path. It will go right past the aldehyde and keep going until it forms a carboxylic acid, which might be something you don't want at all.
And there's a bit of history behind this. For many years, it was actually very difficult for chemists to stop this reaction at the aldehyde stage. Then, in the mid-20th century, mild oxidizing agents like PCC, that's pyridinium chlorochromate, were developed. This was a complete game changer. It finally gave chemists the fine-tuned control they needed, and it totally revolutionized how they could build complex molecules.
Okay, enough theory for now. Let's move from the lab bench to real life and see this controlled oxidation in action. I want you to create a mental picture, okay? Imagine 3 bottles sitting on a lab bench. Bottle 1 has a primary alcohol, Bottle 2 has a secondary, and Bottle 3 has a tertiary alcohol. Now, into each bottle, we add a few drops of an orange-colored oxidizing agent, something like chromic acid. So, what do you see? In the first 2 bottles, the one with primary and the one with secondary alcohol, that orange solution immediately turns green.
That color change is your visual proof. It tells you electrons have been transferred, oxidation has occurred. But what about the third bottle, the one with the tertiary alcohol? Nothing happens. It just stays orange. No reaction. So, this chart here sums it all up beautifully. Primary alcohol, yes, it reacts. Secondary alcohol, yes, it reacts too. But the tertiary alcohol, no reaction. This is the key takeaway from that mental experiment. Now let's go all the way back to that first question I asked you about making medicines in a pharmaceutical lab. This idea of control, it is not just for your textbook or exam. In the real world, a small mistake here, choosing the wrong agent, it can ruin an entire batch of a drug worth lakhs or even crores of rupees.
Look at this flowchart. It shows exactly how it works. Step 1, you start with your specific primary alcohol. Step 2, you carefully add a mild oxidizing agent like PCC. What's the result? You get the exact aldehyde you needed, and you get a lot of it, a high yield. But now what's the fail condition? If the chemist had used a strong agent by mistake, it would have over-oxidized the aldehyde, turning it into a carboxylic acid. The synthesis would have failed completely. The whole batch, gone. This shows you control is absolutely everything.
All right, we're almost at the end, so let's do a quick recap for your exams. Think of this as your master recipe for success in this topic.
So, what are the most important points to take away from our discussion today? Number 1, the core idea. Aldehydes and ketones are prepared by the controlled oxidation of alcohols. Number 2, the key visual. Remember those 3 bottles? Primary and secondary react, you see the green color, but tertiary does not, it stays orange. And number 3, why it all matters. In a real-world application like drug synthesis, precise control isn't just nice to have, it's absolutely essential.
So please, my advice to you is this. Don't just try to blindly memorize a list of reactions. Instead, focus on understanding these 3 things: the core idea, 1 mental picture, and 1 real example. If you can hold on to these 3 points, I can assure you that this topic will feel so much lighter and easier when you face it in your exam. Keep up the good work.